Okay, so welcome back everyone to the 8th edition of the Beyond the Edge seminar series. Today we have Professor Jürgen Jost as a speaker. He's a professor at the Max Planck Institute of Mathematics in the Sciences in Leipzig, and he also has affiliations with the Max Planck Institute of Human Cognitive and Brain Sciences, the Santa Fe Institute, and the Center for Scalable Data Analytics and Artificial Intelligence. Today he will talk about the mathematical theory of hypergraphs, and I will hand it over to you now.
Yeah, thank you very much. So I will speak about hypergraphs, which of course is a subject that you're already quite familiar with through your work with Christian, Rafaela, and then Chris and others. And in fact, I will also describe some of my collaborations with some of those senior scientists. But I hope that my perspective may add a little to what you already know from the supervision by those people. So let's start in a general way. So we are faced with structures when we talk with people in the applied field, but we are not the only ones. So we are competing with physicists. And physicists usually want to develop tools that efficiently identify important and interpretable features, and also they want to have schemes and methods that are easy to compute. We as mathematicians, however, want to derive that also from abstract principles. And that is what makes hypergraphs interesting for us, namely that we can bring in many abstract principles with which to view that. Well, let me start in a very abstract way. Later, of course, I will also describe applications, but let me start in a very abstract way with category theory. We have a very simple category. There's two objects, 1 and 0, and one non-trivial morphism between them from 1 to 0. And then we have a functor from that category to sets. And that is, we have two sets, R and U, and we have a map from H from R to U. And in this talk, I will assume that the sets are finite because that is not an analysis talk. And for our purposes, usually U is a power set of some other set, and that set is called V, and V, of course, should remind you of vertices. So we are looking at sets of vertices. And R stands then for relations. And so for each relation, we associate a set of elements of our vertex set. And then, of course, we assume that every vertex is contained in at least one relation. And so this is a basic hypergraph. That is, a hypergraph would simply be a cover of a vertex set. And of course, if every relation just connects two elements, then we have an ordinary graph. Now from hypergraph, we can construct a simplicial complex. It's check complex. That goes as follows. Now the vertices are the elements of the relations. The vertices of that simplicial complex are the elements of the relation set. That is the subsets of V that express relations. So the vertices of sigma are no longer original vertices V. They are the various subsets that stand in relations. And then when we have a relation, we can see whether it has some overlap with other relations. And when K plus 1 relations have a non-empty overlap, that is they share one or several vertices of our original vertex set, then we insert a simplex. That way we get a simplex, and that is just what is usually called a check complex. And then for a check complex, of course, you can do many things. You can do algebraic topology, and for example, you can compute the Betti numbers of that simplicial complex and declare them as invariants of the hypergraph. That is simple, but that is not yet enough for our purposes, obviously. But nevertheless, in that sense, we can already build upon existing theory. And if we have a simplicial complex, we can associate Laplacians to it. That is what Benno Eckmann did in 1944. He constructed an analog of the Hodge Laplacian in Riemannian geometry for a simplicial complex. And if you have Laplacians, of course, you can look at the eigenvalues. The zero eigenvalues just give you the topological information. The multiplicity of the eigenvalue 0 in a particular dimension equals the corresponding Betti number of the simplicial complex in that dimension. That is, we have an analog of the Hodge theorem. And of course, then one can also look at other eigenvalues, which, for example, I have done with my former student Daniela Horak. But for our purposes, that is not quite enough of a structure. So we enrich the category. Now, we still have the same objects, 1 and 0, but now we assume that we have two non-trivial arrows from 1 to 0. And again, we assume that we have a functor from that category to sets. And so that means now we have two sets, R and U, relations and vertex combinations, but now we have two maps. I call them I and T for initial and terminal. And now this is a directed graph where R is the edge set and U the vertex sets. And U, again, as before, contains the vertex sets. And now we have two arrows, the initial arrow and the terminal arrow, that maps an edge to its initial and its terminal vertex set. Again, we assume that U is a subset of the power set of a vertex set. And now R, relation R in capital R is a hyperedge. And to each hyperedge, we associate two sets of elements of V, namely the input and the output of the hyperedge. And now this is a directed hypergraph. Now, in other words, a directed hypergraph consists of two families of subsets of a vertex set V. And of course, now we get an induced map that maps an input of a hyperedge to its output. But now, in general, this does not induce a simplicial map of the check complexes. Therefore, we need to construct other invariants than those coming from these check complexes. And that is what I will describe here, both in mathematical theory and with regard to applications. But we shall usually ignore the directions. That is, we also consider the reverse direction and then speak of orientations. And we call this a chemical hypergraph. So in other words, in an oriented hypergraph, one hyperedge can carry two orientations, going back or going forth, corresponding to the two directions. Whereas in a directed hypergraph, a hyperedge goes in only one direction. And that was the starting point of my work with Raffaella. Well, here's a picture. On the top, we just have an ordinary hypergraph with just one hyperedge connecting two vertices. Below, we have an oriented hypergraph. So we have one hyperedge that connects the yellow and the orange set of vertices. Here's another example. The hyperflower, that is an example that will also come up later. So we have a group of central vertices, 10 in this example, that are contained in all hyperedges. And each hyperedge then, in addition to those central vertices, also contains a distinct group of peripheral vertices. In that case, each such group contains precisely 3 peripheral vertices. So we have 10 central vertices that are linked by 5 hyperedges to 3 peripheral vertices each. Of course, you can have more complicated configurations. So in particular, the peripheral groups could contain varying numbers of vertices, but this example is good because we can explicitly later on compute the eigenvalues, making use of the symmetry here. Now, before going into the theory, let's consider an example that we are also studying. So we look at chemical space, which means that we look at all chemical substances that are known and that are connected by chemical reactions. So the chemical substances are our vertices, and the reactions are our directed hyperedges. So in other words, the chemical reaction connects a set of educts, the substrates, with a set of products. So the educts are transformed into the products by the chemical reaction. So a reaction is an edge that connects two hypervertices. The educts is one hypervertex, and the product is another hypervertex. So now we can ask many questions. What is possible? The chemist would like to know that. What is currently known? Because substances and reactions keep being discovered. And we can also ask the historical question, how did it evolve from the beginnings more than 200 years ago of modern chemistry to the present situation? So, and that has been studied and recorded. So traditionally, the chemists until the 1970s regularly compiled all the known substances and all the known reactions in two handbooks. One for organic chemistry, the Beilstein handbook, and another one for organometallic and inorganic chemistry, the Gmelin handbook. But in the 1970s, this became too big. And so then the handbooks were bought by Elsevier, the rights were bought by Elsevier, and Elsevier then converted into an electronic database that is regularly updated. Whenever a new substance or new reaction is described in a publication or in a patent application, it goes into the database. And we are one of 5 groups in the world that has access to that database. And already a couple of years ago, there were more than 42 million chemical reactions recorded and more than 20 million substances participating in that reactions. Of course, now we still have more, but the absolute numbers are not the important point. Of course, this is very useful. This is a very precious data set that we can use, and I will describe that a bit, to trace the evolution of a science. It would be great to have something similar for mathematics or physics. But chemists, in that sense, seem to be much more systematic than mathematicians or physicists because they have basic units. The basic units are the substances and reactions. And we don't have anything similar in mathematics or physics that spans the entire field. But now let's look at what we can extract from those data. We have been working on that for a couple of years, and one of our first findings that the red compounds, new substances, grow at an exponential rate. So this is a logarithmic plot, and it was just briefly interrupted by the 2 world wars. Then we had the dips, but it recovered afterwards very strongly, in particular after the Second World War. In the First World War, the dip was more pronounced because before the First World War, chemistry was mostly concentrated in Germany. In the Second World War, it was already more internationally distributed. And we find something similar if we split it up. So we look at organic chemistry, in particular the substances containing carbon. Then we can look at other groups of substances, the alkali metals or the platinum metals, and they all show an exponential increase, a little more fluctuating than the overall picture, which is dominated by the organic substances. So then here we first try to do a statistical fit. So t is time measured in years. And so we have an exponential growth with some variation. And we assume in the basic model that it is regular exponential growth perturbed by some white noise. And we find that we have 3 periods that are slightly different from each other, but the overall growth rate is about 4% per year. That has been maintained by now for more than 200 years. And so that is, of course, very impressive. Our science can grow that regularly in spite of all economic, political, demographic fluctuations or whatever, and also shifts between countries. Because it was in Germany, dominated by German chemistry, and for a long time the Americans dominated, but now, at least in quantitative terms, the Chinese have taken over. But that didn't affect the growth rates. But there were sharp transitions between the growth rates. So until 1860, it evolved with relatively high fluctuations, and then it was dominated by exploratory and mostly inorganic research, and it ended about 1860, or transition took place in 1860, and we speculate that the structural theory of chemistry, that is, you had some insight about the structure of organic molecules, led to a century of guided production, which we call the organic regime, then was clearly bounded by organic substances and reactions. And we already see that the standard deviations, the fluctuations, dropped considerably. Then we had a third regime. There was again a sharp transition in 1980 or 1981, when again the sigma dropped considerably, and we call this the organometallic regime, because then most reactions involve both organic materials and metals, and this is the least exploratory, and it reaches then new corners of the space, of chemical space, characterized by compounds with unusual properties, and of course of unprecedented nanoscales, or of material science, and so on. And so that seems to have been driven by technological change, namely the high throughput methods, where you could test many reactions in parallel in a systematic manner. Now, okay, so that is an important example, and that was our motivation for looking at hypergraphs. But now what can we say as mathematicians? So now, again, I return to the abstract mathematics, but now I'm no longer using category theory. I do something different, namely, whenever you have structures, you can look at functions on that structure, and then you can look at certain relations that involve the neighborhood in the system. So we have our set U, and then we associate a Hilbert space L2 of U, or functions on U, and we may want to give some weight to each U, and then we can define a scalar product of functions on U. Of course, you all know that. It gives us a Hilbert space. And then we let R, or set our relations, operate on that Hilbert space, And so then we define local quantities, rho of U, that encode how the elements of U are related by the operations of R, and we look at their statistics. And the statistics could be curvatures. Probably I will not have enough time to come to curvatures, but that is already one way of proceeding. But here we first want to do something different. If you have a relation with its input and output, the initial part and the terminal part, we can look at the combined effect of the function. So we sum for a function, we sum it over all input vertices, and we subtract the values over all output vertices, and so there's a difference. So what the relation does to the value of the function. Of course, when we exchange initial and terminal vertices, we get a minus sign. And so, of course, in much of algebraic topology, signs are very important. So that is already useful for us. And so to make full use of the sign, we should consider oriented relations. And so then when we change the orientation, we indicate that by a minus sign also on the relation. So r goes to minus r if we go in the opposite direction. Okay, now we have the differences. And they, of course, satisfy some obvious relations. If the terminal set of relation 1 is the initial set of relation 2, the terminal set of relation 2 is the initial set of relation 3, and finally, if it comes back, that is the terminal set of relation 3 is the initial set of relation 1, then if you sum up all the differences, we get 0. There's some simple algebraic structure here already. That is, the difference operator annihilates cycles. And of course, again, that should remind you of algebraic topology, where we want to identify non-trivial cycles. And so the difference helps us to identify them, namely they are the zeros. Now, in order to proceed, we also look at functions on R. So far, we have been looking on functions of U, but now we also look at functions on R, on the relation set. Again, we may have weights, and again, we can define a scalar product. And of course, we use that. We need that to obtain an adjoint of our difference operator, because the difference operator took a relation and then assigned a function on and converted it to a vertex function. I'm sorry, we start with the vertex function, and then we convert it via delta into a function on the relations. So f was a function on the vertices, and delta f is a function on the relations. And now we want to go back, and so therefore we need another scalar product in order to define the adjoint. That is to get away of going from functions on the relation set to functions on the vertex set, and that is our operator delta star that is then defined with the help of these two scalar products. And of course, since delta is antisymmetric, as we noticed, if we go in the opposite direction of relation, we get a minus sign. Therefore, delta star vanishes on symmetric relation functions. And so therefore, it suffices to consider functions on relations that are antisymmetric. That is, a function that for minus r just turns out the value of minus the function on the original relation. Of course, if we want to include symmetric relation functions, we should choose a delta that is not antisymmetric. One could do that, but I'm not pursuing that here. Now we have a boundary operator, delta, and we have its adjoint, a co-boundary operator, and then of course we can combine them in two different ways, and that gives us two operators that we call Laplace operators, analogously to what Ekman had done on simplicial complexes. So if we apply first delta, we go from U to R, and then with delta star, we go back from R to U. So delta U is an operator on L2 of U, and likewise delta R, where we take the product in the opposite direction, gives us a function on L2 of R. We have two Laplace operators. Of course, with Laplace operators, we are very happy because now we have operators that operate on the same space, so we can look at the eigenvalues. Of course, these are linear operators, so we are in the realm of linear algebra, and we can do computations relatively easily. And of course, by these obvious relations, the operators are both symmetric and they are all non-negative because in the middle you have a square. If f is equal to g, we have a square. Or if gamma is equal to omega, we have a square. And so therefore both operators are non-negative. And being symmetric and non-negative, they have real and non-negative eigenvalues. And also by basic linear algebra, if you take the product, two products of such operators AB and BA, the non-zero eigenvalues coincide. The multiplicity of the eigenvalue 0 may be different. After all, we may have differently many hyperedges and hypervertices, and so the dimensions on the spaces on which the operator are different. So in particular, the number of eigenvalues is different, but that only comes from the multiplicity of the eigenvalue 0. All the other eigenvalues coincide. That, of course, is useful for computational schemes. When we want to compute the non-zero eigenvalues, we could take either operator. So, and this then yields the Laplace operator for hypergraphs that I had developed with Raffaella, and in particular Raffaella in her thesis developed that. So we need to specify certain things. We need to specify the weights. For this particular operator, of course, the scheme is general, and you can look at the Laplace operators for other choices of weights. But here we give weight 1 to the hyperedges, and then we give a weight for each vertex where we look at the number of hyperedges that it is contained in, and we look at the size of each hyperedge. So for each hyperedge, we look at how many other vertices it contains besides the vertex that we are looking at, and then we sum up these numbers for all the hyperedges containing that vertex. So that is our choice of weight here. And then with those weights, as a scheme that I already described, we define a scalar product for functions on hyperedges and a scalar product for function defined on vertices based on the weights. Then we have the boundary operator, mapping for functions defined on vertex sets, mapping them to functions defined on hyperedges. And we have the co-boundary operator from our scalar products. And then we have the two Laplace operators as the two different compositions of the boundary and the co-boundary operator. Thus, we are implementing the scheme now more concretely that I had abstractly described before. So here again, our scalar products on hyperedges and on vertices. We have the boundary operator. To repeat that, we just look at the sum of the values at the input of a hyperedge and subtract the sum of the values at the output of the hyperedge. We have the adjoint operator, which now takes this form because of the weights we define by the hyperedge degree of the vertex. But for each vertex, we look at the values of all hyperedge functions that contain that vertex as an input, and we subtract the values of all hyperedge functions that contain that vertex as among its outputs. Then we have the Laplace operators. Now that looks a little complicated, but at least I want to show you the formula. You can look at it in leisure because this meeting is recorded. I don't want to go into all the terms here. I just want to recall what that means when we have an ordinary graph because then it's simpler. Namely, when we have a graph with vertex set V and edge set E, then the degree of a vertex is just the number of edges it is contained in. And then we have the Laplace operator that takes the value of the function at the vertex itself and subtracts the average of the vertices at its neighbors. And likewise, on the edge set, then for each edge, we look at all vertices that are contained in the initial set of the edge, takes the average of the values there and subtract the corresponding average for all values at vertices that are contained in the other set. So now, as already said, the two operators have the same eigenvalues and they have the same non-zero eigenvalues, and therefore the multiplicity of the eigenvalues, the difference of the multiplicities of the eigenvalue 0, thus gives us a difference of the dimension of the spaces that they're operating on. So here, thus the difference of the eigenvalue 0 of delta 0 on the vertex set and delta 1 on the edge set is thus the number of vertices minus the number of edges. That is the Euler characteristic of the graph. Now, in general, when we go back to hypergraphs, then the initial and the terminal set need not be disjoint. Even for graphs, we might assume that we have closed loops, that is, edges that start and end at the same vertex. And this cause an eigenvalue 0. That's because of the chemical interpretation, we call them catalysts. So the catalyst is a substance that enters a reaction, participates in it, but is not changed in it, that is still present in the products. So in mathematical terms, it's contained both in the input set and in the output set of the reaction. And then catalysts cause an eigenvalue 0 for delta 0, and closed systems of reactions, that is, when we start with something, undergo a couple of reactions and return to the same set in the end, we get an eigenvalue 0 for delta 1. And bipartiteness in general causes large eigenvalues. For the graph Laplacian, we have the maximal eigenvalue 2, and that is realized if and only if the graph is bipartite. Now again, let's look at the hyperflower, that example that we had seen already earlier. So we have a group of central vertices contained in all hyperedges, and then we have also distinct groups of peripheral vertices, and they all have the same size. Here, C is 10, L is 5, and T is 3, but we could work with an arbitrary number here. The important point is just that we have the symmetry. Now here it is again. And so now we want to identify the spectrum. So first of all, we can look at a function that is -1 on central nodes and +1 on peripheral nodes. When one computes it, it has the eigenvalue C plus T, so C is the number of central vertices and T is the number of peripheral vertices in each hyperedge. And so if we compute it, of course, the computation is an exercise for which I don't go here. We get that eigenvalue, and that is a relatively large eigenvalue. And so the message here is that opposite behavior, we have opposite values at the center and at the periphery, and that creates large eigenvalues. Then we can also look at functions that are just +1 on one leaf and -1 on another, and 0 everywhere else, so including the central vertices. Again, this gives an eigenvalue, which is equal to T divided by C plus T minus 1. And of course, we have L minus 1, such linearly independent eigenfunctions, because we have else such leaves. This is a balanced behavior. What is happening on one leaf is balanced by what is happening at the other leaf, and that creates intermediate eigenvalues. And the remaining eigenfunctions simply have the eigenvalue 0. And they are 1 over c with some normalization. The normalization, of course, is arbitrary. They are 1 over c on the central nodes and 1 over t on the peripheral nodes. And so here the sign is not changing, and that gives the smallest possible eigenvalue 0. So there we already see the typical behavior. In particular, we see what we can read off from knowing the eigenvalues. And then the remaining ones are even simpler. We just take k plus 1 on one node and minus 1 on another node of the same component, be it a center or leaf, and 0 everywhere else. And then we have still the number of such functions, and altogether we have enough functions to equal the dimension of the space, so we have determined the entire spectrum. But here we have two inputs or outputs that compensate each other. And so in this symmetric example, we can relatively easily guess by making an appropriate ansatz in each case all the eigenvalues and eigenfunctions. Now, let's look at some other application. Well, now we again go into a different direction, namely into something that physicists and nonlinear dynamics have been studying, and we have extended that. So again, there's some background. Many years ago, the Japanese physicist Kunihiko Kaneko discovered that chaotic oscillators that are diffusively coupled can synchronize. And that is a very surprising discovery, because chaotic means that it looks almost random, and it is very difficult to predict and control. But when you couple two or more chaotic oscillators in an appropriate way, then they may still remain chaotic, but they can synchronize. That is, their behavior is identical. Of course, sometimes you see that in applications. So if crowds of people, whatever, at soccer matches, every guy may be completely chaotic, but then they may synchronize their behavior, their songs and applauses and whatever, or create waves also. So that is from individual chaotic actors, you can get quite regular behavior at a collective level. So now let's consider that in more mathematical terms. So first, again, the traditional graph setting. We have the vertex set of a graph. And now, of course, since we have oscillators, we also need time. And we choose discrete time. And so we consider functions on the vertex set at each time n. And so here's the evolution. So first of all, we have a term for some function f here, which will be a chaos generating function. We will see some example later on. But then we have diffusive coupling. So we take the Laplace operator of f. It's the same vertex at the same time. That, of course, looks at the average of the value, compares the value at the vertex with the average of the values at its neighbor. So it was the point of the Laplace operator, and we have some coupling strength epsilon. And again, we recall the Laplace operator here. It compares the value at the vertex with the average of the values at the neighbors. And of course, now we do that for every time. And so synchronization means that the value of the function at each fixed time is the same for all vertices. And of course, initially they may start differently, so they will not synchronize immediately, but they may synchronize after some time and zero has elapsed. And as already said, f can be a chaotic function or should be a chaotic function here, like the tent map. Now here's a tent map again. So if x is between 0 and 1/2, it doubles the value. If it's between 1/2 and 1, it still doubles the value, but subtracts that from 2 in order to fold it back into the unit interval. There's a map from the unit interval to itself, which of course amplifies differences. So local differences are multiplied by a factor of 2 at each time step, and that of course leads to chaotic dynamics. We compared also with the identity function, and we notice that the two graphs in fact meet at the value x equal to 2/3. Of course, we can attenuate it a little, and we can multiply it by some sigma, and we can compute the Lyapunov exponent, which is in the logarithm of 2 sigma. And since we are looking at positive values here, it may be in particular for sigma equal bigger than 1/2, it is positive, and so we have chaotic behavior. And so this dynamic iteration here of this function here then generates chaotic behavior if sigma is sufficiently large. So that is what Kaneko did. In a slight reformulation that is not completely identical to his scheme, but that is a way that I reformulated it many years ago with the postdoc. So now we find that there's a sufficient condition for synchronization, namely that this quantity has to be smaller than 1. So lambda k are the eigenvalues of the Laplace operator. And so what counts only the smallest eigenvalue and the largest eigenvalue. For the smallest eigenvalue, this is relatively large. In particular, except for the eigenvalue 0, of course, the eigenvalue 0 corresponds to constant functions, that is to synchronized behavior. But for smallest positive eigenvalue here, this is 1 minus epsilon times the smallest eigenvalue, so this is large. And if you have another eigenvalue that is close to 2 or equal to 2, then this in absolute value gets close to 2 minus 1. The absolute value, again, is relatively large. And here you have the Lyapunov exponent, e to the Lyapunov exponent. So in other words, since the Lyapunov exponent in chaotic behavior is positive, this is a positive contribution. And to make it smaller than 1, the absolute value of this quantity has to be sufficiently small, sufficiently smaller than 1 to make the product smaller than 1. And so, as I said, we only need to look at the smallest non-zero and the largest eigenvalue, because for the eigenvalue lambda equal to 0 corresponds to constant behavior, and that is precisely the synchronized state where it is constant with respect to the vertices. So that is a simple condition that we identified. As I already said, synchronization of coupled chaotic oscillators is a very surprising phenomenon. Each chaotic oscillator still is chaotic, but they all do the same. But nevertheless, the global state where everybody is doing the same may not be so interesting. It may even be dangerous. So these oscillators can, of course, also happen in your brain. So neurons or neuronal groups in certain regimes can be chaotic. They are coupled. so synapses between neurons. And of course, you don't want them to do all the same because otherwise you would get epileptic seizures. So in other words, we want to have something within that paradigm of coupling chaotic oscillators, but something that can create richer dynamics at the collective level than simple synchronization. And that is a project that I did with Christian Kühn and his student Tobias Böhle and with Raffaella a couple of years ago. Namely, we diffusively coupled oscillators no longer on graphs, but on hypergraphs. So here again is our hypergraph Laplacian, the one that I had introduced earlier, with all the details here. So maybe we look a little bit at the details. So we have a function on a vertex set. So then we look at all hyperedges that contain V, that vertex V, first as an input. Then we look at all other vertices V prime that are in the input set, of the same hyperedge. We sum up all the values of the function here. Then we look at all vertices that are in the output set of that hyperedge that contains V at its input and subtract the values there. And then we do the opposite for those hyperedges that contain V in its output set. So now, since we are summing up here over all vertices that are in the same input set and summing over all vertices that are in the same output set, this operator, in contrast to the Laplace operator on graphs, in general no longer satisfies the maximum principle. So here again is our normalization factor that is not really so important. So in other words, we look at the flow, so hyperedges, where V is the input, minus the flow, so hyperedges, where V is an output. So that is the interpretation here. We are looking at flows through hyperedges for each vertex. At each vertex, we look what is coming in minus what is going out with suitable averages. So we can also rewrite it in terms of a function for a vertex and a hyperedge that outputs 1 if V is in the input and outputs -1 if V is in the output of that hyperedge and 0 else. And then we can somehow simplify the expression for the Laplace operator. So here we consider those that other vertices that are together with V, either in the input or an output of a hyperedge. And here we consider those vertices that when V is an input are in the output, and if V is an output are in the input. And here we take the positive of the sum, and here we take the negative sum. So we are looking at flows through vertices. And so again, we have our chaotic function, and we now diffusively couple it with our Laplace operator here that I have described extensively with some coupling strength epsilon. And then again, we take the hyperflower, our beloved example. Then we see what happens. So now the colors, so all the figures were created by Tobias Böhle. So the colors indicate sampling times and are used periodically. So we have 4 or 5 different colors here. So maybe you start with the red color, and on the vertical axis we record the value of the state function. So at one red time, all these vertices here have this value close to 1. At another time they have a much smaller value here. And we already see that we get some synchronized behavior on the central vertices. So these here are the central vertices here, and here are the peripheral vertices. And so we already see some interesting behavior. All the central vertices are synchronized among themselves, and all the peripheral vertices are synchronized among themselves according all the peripheral parts of the leaves, but they behave differently. Center and periphery behave differently. That already is a richer behavior than we would get on a graph. Here we see something different. Now, the central vertices are still synchronized, and the values fluctuate now only in a very small range. The chaotic behavior is much dampened, whereas the peripheral vertices fluctuate wildly. There's no synchronization there, neither within leaves nor between leaves. Here, now we see again something interesting. So we see synchronization in the center and within each leaf, but not between leaves. So each leaf is synchronized, but all the leaves behave differently, and still the behavior is chaotic. Here is again another example. Again, the center is quite regular. Now, within each leaf, two of the vertices are synchronized, and the third one is different. It's the same pattern within each leaf, but again, between leaves, the behavior is different. So one of the vertices has a smaller range, is different from the two others, whereas the two others are still fluctuating, but there's already some kind of time periodicity here, because the green and the red times cover a different range than the light and the dark blue ones. Okay, now I have a few more minutes, and I will just very briefly indicate something else. Namely, much of what we do on graphs or hypergraphs in geometry is inspired by Riemannian geometry. And of course, both graphs or hypergraphs on one hand and Riemannian manifolds on the other hand carry metric or geometric structures. And it has been an important research direction in recent years to extend concepts that were originally developed in Riemannian geometry to more general metric spaces. This kind of a historical irony, because Riemannian geometry is a much more involved or complex structure than the metric structure of a graph, but mathematical discoveries are not always made in their logical order. And so Riemannian geometry is a very well-developed subject, starting with Riemann's habilitation address in 1854. And in particular, the basic concept of Riemannian geometry is curvature. And curvature as a measure of information spreading has been also developed in graph theory, inspired again by the concepts in Riemannian geometry, and applied quite successfully to network analysis. And now, of course, naturally, we wanted to develop something similar for hypergraphs and apply that to chemical reaction networks. And so that is one of our current projects. We are studying that really in much detail with the chemical reaction networks, but I don't have the time to go into that here. Just a very brief summary. In Riemannian geometry, you have three types of curvature concepts. You have the sectional curvature, already introduced by Riemann. Then we have the Ricci curvature, which is some kind of contraction introduced by Ricci. And from that, by another contraction, you get the scalar curvature. And we have been developing both sectional and Ricci curvatures. Scalar curvatures are too weak in there in order to tell us much. But here I just want to very briefly concentrate on Ricci curvatures. And in Riemannian geometry, Ricci curvatures are evaluated on tangent vectors. And since a vector is determined by 2 points, and therefore for a graph, the analog of the tangent vector would be a direction that is an edge that connects two components, and we have then developed that And for hypergraphs, then we assign Ritchie curvatures to hyperedges. And Ritchie curvature controls expansion properties of volumes of stochastic processes because it averages over the divergence of geodesic curves. And in particular, therefore, lower bounds on the Ritchie curvature carry geometric content, whereas upper bounds don't carry anything because my student Jochen Lohkamp in his thesis proved that every manifold of dimension at least 3 carries a metric with negative Ritchie curvature. And for example, the Ritchie curvature expresses the relation between the volume of a ball and the area of its boundary. And in other words, when you have a lower Ritchie curvature bound, the interior of a ball controls its boundary. And so these are local properties, but if such properties hold everywhere locally, that is, we have a lower bound on the Ritchie curvature, and if we can then derive the same results everywhere, then we get global geometric consequences. So, for example, if the Ritchie curvature is bounded from below for remaining manifolds, the Peirce-Betti number vanishes, and we get an explicit lower bound for the first non-zero Laplace eigenvalue. And so, since I'm coming to the end, I just want to point out that now the notions of Ritchie curvatures for graphs that were developed by Olivier, Foreman, Bakri-Emery, and others, and the notions of Ritchie curvatures for hypergraphs that in particular were developed within my group, then imply similar or analogous properties for graphs and hypergraphs. And then we looked at the statistics of such curvatures, and in order to extract information about the global properties of a network. But since I'm coming to the end here, I will not go into that anymore. I will just acknowledge my collaborators. I already mentioned Rafaela Mulas, with whom I developed the Laplace operator for hypergraphs, and then Christian Kühn and Tobias Böhle, who together with Rafaela and me looked at the diffusively coupled chaotic dynamics on hypergraphs. Then for other projects, in particular for the curvatures, I worked with other people, and including Dong Zhang from Beijing, Wilma Leal, former graduate student who is now in Florida, and Mazir Edi, also a former graduate student who is now at SCATS AI in Leipzig. And the chemistry project was done with Duc, who is now in Klagenfurt. He was also a postdoc in my group with Wilma, already mentioned, and with Guillermo Restrepo, who's still in Leipzig, and with Peter Stadler, who's the bioinformatics chair at Leipzig University. So I've reached the end of my time. Just thank you for your attention. Of course, I should be happy to answer questions in case you have any.
Okay, thank you very much. It was a very good talk. Yes, so if anyone has a question, please unmute yourself and you can ask the question. Otherwise, I have a question. Okay, so I heard a little bit already about the Laplacian for hypergraphs. So you mentioned it for oriented hypergraphs, and I was wondering how well they are at distinguishing non-isometric hypergraphs. Do you know if there's any results on that?
Well, I mean, that's already an important question for graphs. Yeah, and similar for remaining manifolds. If you know the spectrum of the Laplace operator on a structure, do you know that structure up to isometry? In general, the answer is no. In Riemannian geometry, that took quite a number of years. I think the first example was constructed by Milnor on certain 16-dimensional tori. Then other examples were found up to dimension 2. On graphs, it's a little easier. Just look at the spectrum on vertices. If you take complete bipartite graphs, Yeah, that is, you have two sets of vertices, V1 and V2, and every vertex in V1 is connected with every vertex in V2, but there are no connections inside any class. It's a complete bipartite graph. And for those, the spectrum thus consists of the eigenvalue 0 for the constant functions, the eigenvalue 2 because of bipartiteness, and all the other eigenvalues are 1. And in particular, if V0 of V1 has n1 elements and V2 has n2 elements, then you have n1 plus n2 minus 2 eigenvalues 1. And so it only depends on the sum, n1 plus n2. So it doesn't matter how you distribute the vertices among the two classes. So we could have a simple case where one class just contains one vertex, then you have a star graph, all the others are contained in the other class, or you could have a situation where both classes contain the same number of vertices. As long as n1 plus s2 is the same, the spectrum is also the same. So that's a very simple example. Yeah, of course, then if you also look at the operator on edges, yeah, then of course the number of edges is different. So the multiplicity of the eigenvalue 0 is different. So you can distinguish it if you look at both of them at the same time, but you can then construct more elaborate examples where even if you take both Laplacians, that in particular, if you have the same number of vertices and same number of edges, you can still find graphs that are not isomorphic but still have the same spectrum. So already for graphs, that is complicated. And then, of course, for hypergraphs, it is even more complicated. But I think there's a conceptual reason behind that, namely checking the isomorphism of graphs is an NP-hard problem. Whereas computing eigenvalues can be done with linear algebra. Yeah, and so therefore, conceptually, it should not really be possible to solve an NP-hard problem just by tools from linear algebra. And that's why one would not expect that the spectrum characterizes an object completely, a discrete object completely, but nevertheless, the point is that the spectrum contains very important information. For example, for graphs, you have the analog of the Chiga inequality. That is, the first eigenvalue controls the cohesion of the graph. Yeah, and as already said, whether or not the eigenvalue 2 is present tells you whether or not the graph is bipartite.
Okay. Okay. All right. Thank you. If there are no more questions, then I think we stop the recording.